Welcome back. So last time we were discussing about databases. We were discussing about how do you actually create a database and so on. And then we transitioned into looking at the individual elemental descriptors, where we had a bit of discussion on periodic tables and just tried to give you some sort of examples of the type of information you can extract from the periodic table. So once we have an idea of what the elemental descriptors could be, now we can actually start getting into the weeds in a little bit more detailed manner. And so today what we are going to do, we will be taking up this topic of how do we do feature engineering, how do we actually featureize in materials informatics. Now, as far as looking at the features and the predictions of materials informatics is concerned, you can kind of think of the workflow in this way, that you have to start with an input query. So the input query could be some form of input that you give to your machine learning code, machine learning model, based on which it is going to calculate and give you the output. But before it gets to the output, it actually needs to do some amount of training or some amount of fitting. And the way it will do the fitting is it is going to take and call upon the descriptors which describe the input. And of course, when you are training the model as the modeler, it is your task to select what would be the best descriptors. And these descriptors are really what we call the features. And so once you give your input, the model will then pull up the descriptors and evaluate the descriptors for that particular input. And then based on how it has been trained, it is going to give you the output result. So for example, if you want to describe, let us say your problem has the element iron in it and you want to describe iron. So there are lots of ways in which one can describe iron. So you can use the atomic number, you can use the atomic weight, you can use the number of valence electrons, the crystal structure of iron. Let's say we are just talking at room temperatures and normal pressure. So we know what crystal structure it is, right? So what you see over here is I have color coded these features. So something like atomic number, that is going to be fairly unique to iron. No other element is going to have the same atomic number. Similarly, the atomic weight is also unique to iron. No other element has the exact same atomic weight. If you look at the features which I have highlighted in blue, you will notice that things like the number of valence electrons is not unique to any particular element. So you could have multiple elements having the same number of valence electrons. Similarly, if you look at crystal structure, if we are talking about alpha ferrite at room temperature, that is BCC, but then there are lots of other elements and lots of other metals which have the BCC crystal structure at room temperature. So when you look at the descriptors, you will find that some of the descriptors are unique descriptors, whereas a few other of these descriptors, they are not unique, but nonetheless, in combination of many such descriptors, as well as in combination with some of the unique descriptors, it is still end up defining your material. Now, the advantage of the unique descriptors is the moment you give this unique descriptors, it's very easy to figure out what element you're talking about. Whereas if you're using some of the other ones, like the number of valence electrons or the crystal structure, what that does is ends up specifying some sort of a unique class to which this particular element belongs, right? So if I specify the crystal structure of iron at room temperatures as body-centered cubic, I am essentially saying that iron falls into the group of elements which has got a body-centered cubic crystal structure at the room temperature. So many times when we are dealing with different types of problems, understanding which class the material belongs to can also be useful. Whereas obviously having the unique descriptors is always going to be useful because you can identify your input quite clearly that way. Now, the choice of the appropriate features is going to be extremely important. You don't want and get into a situation where you add in a large number of features. Sometime back, we were actually describing that machine learning is, in case of materials, is in most part a sparse data problem. And then what we highlighted was, in case of dealing with those sparse data problem, the domain knowledge is very important. And so it is really useful if you can use your domain knowledge and cut down the number of features just by understanding the physics of the problem. So if you have less number of features, the advantage is it is going to help reduce the complexity of the model. It is going to help you interpret your model in a much easier manner, and it is also going to ensure that the chances of overfitting your data is also less. If you are having more number of features, essentially what you are doing is you are creating more number of variables with which the fitting can be done. And so as you increase more number of variables with respect to the number of data points that you have got, the chances of force fitting increases, and therefore that might actually result in overfitting. So if you can lower the number of features, by all means lower the number of features. But I understand that I'm not telling you that when I say that lower the number of features, you should arbitrarily lower the number of features. Use as many as needed, but no more. Now, when we talk about feature engineering, it is basically the process by which you are selecting, manipulating, and transforming your raw data into features, which can be then put in a usable form for machine learning. So in case of materials informatics, as I mentioned, we will be relying quite a bit on the domain knowledge while doing the feature engineering, and that really is the purpose for going over all of these basic concepts like that of periodic table and basic thermodynamics and so on and so forth. Now, if you look at different types of engineered features, I'll give you some examples. So the first one, of course, is you can do numerical transformations. So this is where you basically do some sort of scaling or normalization. And as you have probably learned in the earlier lectures given by Professor Biswas, that scaling and normalization of the data can be actually quite useful, especially if you have a situation where the features that describe your data can take a huge range of values. So if in one case the overall permissible range is very large, and the other case the overall permissible range is very small, it is always a good idea if you end up doing some sort of a normalization of your data. So that is the first way in which you are engineering the features. You already have some features, you are simply normalizing it. The second way is to do some sort of a category encoding. So here basically this one-hot encoding is a good example of it. We have not covered one-hot encoding yet, but we will be taking one-hot encoding up very slowly. Then one can also look at the clustering tendencies in your data, and then you can end up categorizing the data. You can start associating some category-based labels in your data, and that would be another way in which you will engineer the features. The fourth one is when you take the averages. So group aggregated values, basically what you do, if you have the composition as an input, you know what is the fraction of each element. You simply take a composition weighted average of whatever feature you are looking at, whether that is the atomic radius, whether that is the valence electron concentration, whether that is the electronegativity. It is really up to you which feature you are choosing, but you can do a composition weighted averaging. So this works pretty well with the relatively simple elemental features like electronegativity and melting temperature and so on. Then you can also do some sort of physical construction of the features. So basically what I mean over here is you will be using the well understood physics in order to come up with new features. And a good example of that is when you use thermodynamic potentials, for example, the formation enthalpy, right? So what you are doing when you are computing the formation enthalpy for a given composition is you are taking cognizance of all the elemental input along with the composition, and you are using your knowledge of how those elements start interacting with each other in order to create a thermodynamic potential like the formation enthalpy. So this is another thing that we are going to take up in the next lecture. And finally, you might end up finding that you have got too many features. So each feature is like an added dimension to your problem, and therefore what you want to do is you want to reduce the dimensionality of your problem. You want to reduce the number of features, and one of the ways of doing that is by adopting the principal component analysis. So when we talk about image-based machine learning a little bit later on, when we are dealing with structures and microstructures, that is where we will come across principal component analysis, and we will take that up in more detail at that juncture. Now we talked about one-hot encoding, and this is actually a very useful way of featurizing in materials informatics, especially when you are looking at categorizing something. So one-hot encoding is used for transforming categorical data into numerical data. So for example, if you have something like the crystal structure, you know that the crystal structure is face-centered cubic or hexagonal, close-packed or body-centered cubic. The question is, just by adding this words or letters, it does not really help you that much in solving the machine learning problem. You want to transform all of this into something which is numeric so that you can actually train your model more effectively. So essentially, let me just explain this with a little example. So supposing you have got a database of materials and you want to predict some properties based on what type of material it is, whether it's a metallic material, whether it's a polymeric material, whether it is ceramic material. The nature of bonding is different in all three types of materials, and therefore certain properties are characteristics of metals. For example, if you're looking at ductility, the ceramics are not going to be that ductile, right? And so similarly, the bonding in polymers is also different. So if we want to classify the data and assign the category of metal, ceramic and polymer, what we do is we will go ahead and give metals a value of, let's say, 0. Ceramics can be assigned a value of 1, polymers can be assigned a value of 2. Now it is not necessary that you assign them values of 1 for ceramics and 0 for metals. You might actually interchange it. You might give a value of 0 to the ceramics, 1 to the metals, 2 to the polymers, whatever it is. It's your choice. But the point is, essentially what you are doing in case of one-hot encoding is you are assigning a numerical data to something which is essentially a categorical data. Now there are lots of advantages of doing one-hot encoding. So the first advantage, of course, is it is going to allow the use of categorical data in models which require some form of a numerical input, because you have already assigned a number to that particular category. And so in essence, this is now going to allow you to use more of the data that is available to you. And so that's always a good thing as far as your machine learning model is concerned. Secondly, it is also going to ensure that you start avoiding the ordinality issue. And so ordinality issue, basically that happens. So let us say you've got certain different categories or classes already mentioned. And there might be a tendency in within a specific class, you have some sort of a ordered list. And then the ordered list may not be necessarily something you want. So if you now start assigning the same numbers to all of the members of that class, this issue of ordering, this issue of ordinality goes away. So this is another way in which one-hot encoding can really be useful. But at the same time, you've got some drawbacks of this process as well. So while one-hot encoding can indeed enlarge your database, it can add to your database, it can also increase the dimensionality of your problem. And so once the dimensionality of your problem goes up, the complexity of the model also goes up. So this can be a potential disadvantage. With one-hot encoding, because the very advantage you get by bypassing the ordering or bypassing the ordinality problem also means that a lot of the data starts getting collapsed into a single point. And so that can again result because you are basically artificially clustering your data. So that can again result in some issue. And so when you have a situation where the dimensionality of the problem has increased, but at the same time you have collapsed a lot of data into a single point, essentially making it like a sparse data, that can result in overfitting. So you have to be very careful when you are using one-hot encoding. There are certain cases where one-hot encoding can be very useful, and there are some cases where one-hot encoding can be a little bit problematic. So now when we try to featurize our problem, essentially the way we look at things is we give some form of input, we have featurized the problem, and we need to start predicting the output. Typically the type of output we are interested in materials informatics could be the phase information or the structure information of a material. It can also be the properties of the materials. So if we have a material with a new chemistry which has not been explored, by using machine learning, can we start predicting the properties? So when we do this type of predictions, it is useful to understand the different types of properties the material can have. So by and large, what we do, we can describe the properties, we can divide the properties into intrinsic properties and extrinsic properties. So when we talk about intrinsic properties, these are properties which arise primarily due to the chemical composition, due to the bonding and structure. And so these properties are really inherent to the materials. So these are not properties which are functions of processing conditions. So at this point, maybe you can pause the video and start to come up with some examples of intrinsic properties. So intrinsic properties could be something like, let us say, the band gap of a material. So once your chemical composition is fixed and you have not done processing in any funky way, the structure is fixed, so your band gap is going to emerge automatically. The other type of properties is extrinsic properties. So these are the type of properties which you can actually tune by how you are making the material. Meaning you can start with the same alloy chemistry, the same material chemistry, the same stoichiometry. How you make it, at what temperatures you are heat treating it, whether it has got a large grain size or a small grain size. By controlling all of those things by processing, you can start tuning the property of the material. So once again, go ahead, pause the video and think of some suitable examples. So some examples of extrinsic properties could be things like, let us say, the yield strength, or it could be something like the hardness of a material. So depending on what the grain size is, all of these properties can change, and you can tune the grain size by tuning the processing method. Now, while we think in terms of intrinsic properties and extrinsic properties, it has to be acknowledged that in a few rare cases, you will also have a little bit of interplay between both of these properties. So for example, take this case of color. Now you would imagine that the color of a material is going to be an intrinsic property. Once you know what element it is, it has got a certain characteristic color. So for instance, if you think in terms of gold, gold has got a certain characteristic color which we call golden yellow. Now if you take the same gold and then process in such a way that instead of having large blocks of gold, you now start having lots and lots of nanoparticles of gold. So once you get into this quantum confinement type of situation, you will see that the color of gold also starts changing, and what you see is gold changes the color from the golden yellow to red. So what you have done, you have not changed the element, you have however changed how you process in order to get the final product with gold, and by doing that you have changed the color. So sometimes properties which often look like intrinsic properties can actually be modified to some extent by processing. So from this discussion, I want you to take away two basic things, that we have got two knobs which you can tune and turn in order to control the properties of materials. The first knob is the chemistry of the material or the composition of the material itself, and the second knob is what type of processing method you are using. So when I am referring to the chemistry of the material, what I basically say is you can change the chemical composition by doing some form of doping or some form of substitution, and that is going to affect the intrinsic properties. Or you could apply the conditions of temperature, pressure, stress, and so on, how you process the material, and that starts affecting the extrinsic properties. Now, as it turns out, this first one we simply say is a function of material composition. The second one is a function of structure. And as it turns out, when we talk about structure, this is actually a fairly complex thing in itself, because structure of the material exists at different level. At a very small scale, we can think in terms of the electronic structures. And when we look at this electronic structure of materials, when we do the electronic structure calculations, most of it is done at a certain temperature and under equilibrium condition. And so electronic structure, we are not really changing too much, because when we do the calculations, typically, we don't bring in the effect of processing or anything into that. The crystal structure is somewhere in between. Depending on how much pressure you are applying, what temperature you are heating to, you can actually change the crystal structure. And the microstructure is again the type of structure which is very sensitive to your processing conditions. So these are the different flexibilities you will get when you are trying to make a material. Now, why is this important? Because once you understand what flexibilities you have got, you can tune and you can explore your predictive space accordingly. So let us now take some sort of examples, and what we will do is we'll get into this problem of featurizing the material, and we will start with this concept of composition based feature vectors, which we had briefly discussed below. So supposing I have got an entire collection of elements shown over here. So these elements are going to be very uniquely specified the moment you specify the atomic number or atomic weight. So what I can now do, I can start constructing a feature vector. Each of these features are one dimension or one component of the vector, right? So when I look at aluminum, I have a feature vector which says 13, that's the atomic number, 26.982, that's the atomic weight, 3, that's the valence electron concentration, and so on. Similarly, if I describe iron, I have a different feature vectors. So basically, I have got different descriptors for aluminum and iron. Now, when I'm combining them in order to form a compound or an alloy, I am doing so by mixing them in certain elemental proportions. So Ni3Si, for example, has got 3 units of nickel and 1 unit of silicon. So the way I compute the feature vector for this particular compound is by taking a composition weighted average. So in case of Ni3Si, I am going to take 0.75 times the atomic number of nickel, which is 21, and 0.25 times the atomic number of silicon, which is going to be 3.5, and so the total atomic number, the overall atomic number, comes out as 24.5. Similarly, I can do the same for atomic weight, I can do the same for the valence electron concentration, the melting temperature, and the radius. I can again do the same thing if I am trying to compute the feature vectors for iron aluminide. So for FeAl, I am going to take 50% of Fe, which is 13, and again 50% of aluminum, which is 6.5. And so that gives me the composition weighted average atomic number as 19.5. And similarly, you can calculate the atomic weight, valence electron concentration, melting temperature, and radius. Now, what is interesting is you might actually start with elements having different features, elemental features, but when you mix them, because you are doing a composition weighted averaging, it is no longer essential that the resultant features will be identical, because we are doing some amount of composition averaging over here. So there are a couple of ways of going about this. You can create this composition based feature vectors yourself, or you can use a featurizer such as Olenek or Mat2Vec. So we are going to talk a little bit about Olenek, Mat2Vec, and other types of featurizers in the next video, in the second part of this lecture. We also had a short discussion on MatMiner, and so MatMiner also has an option for featurization, and then one can also use this CBFV, the composition based feature vector package. And so you can actually go to this website over here and you can download this composition based feature vector package. And again, this is very easy to install. You can do a pip install, and then after that, whether you work with Jupyter Notebook or Spider, it doesn't really matter. You can actually use the composition based feature vector package. I kind of like it when I'm using it with Spider, because the Spider also has this inbuilt variable explorer, and so you can actually use the variable explorer and then see how the different features are changing. And within this CBFE package, there are a good number of featurization schemes. We are again going to talk about these schemes in a bit, but yeah, this is a really useful package to have if you're doing materials informatics. So just to give you an idea as to how this thing works, basically what we are going to do, the first thing you want to do is, after you have installed CBFE, you want to import CBFE, specifically the part where the input is given in terms of composition. So you simply import CBFE, and then you of course have to bring in the data frame, so you bring in pandas, and after that what you do, the first step is you will go ahead and read your databases. So here I have got a database on high entropy alloys, which I have labeled as db_HEA_phases. So it's a CSV type of database. So once you grab the data, you want to save that in a pandas data frame. And then basically what we are doing is we will be saving this data frame to one sort of a database. And so I'm just saving it in JSON simply because I can. I'll also want to show you how a JSON file looks at, because we had a little bit of discussion about the different file formats for databases earlier on. Okay, so basically now what I've done, I have simply converted the CSV file into JSON. It is, by the way, not needed to convert CSV file into JSON for this type of work, but nonetheless, I have done that. Just to show that you can do this type of file conversion. So once you read your file, you basically load that into a pandas database, and then after that what you do, you will simply try to parse out the data that you have got in terms of the formula, which is your input, and the target, whatever that target can be. So you can actually have multiple target values if you have a machine learning model which gives you multiple target values, by simply using the extend target type of function which you have within this particular library. And then after that, what you do is you will simply generate the features as a function of composition. So the arguments that this command basically takes is your pandas data frame that you have loaded and which featurizer you are using. So in this case, this is for the Olenek. So as you use this Olenek featurizer, you will see that you have got bunch of different features: atomic number, atomic weight, average period, average group, and so on and so forth. You have a pretty large number, to more than 200 features actually in case of Olenek. The index over here, this simply refers to the row number of the input composition that you had in your data set. Now, because you have so many large number of features, and Olenek is actually a simple featurizer, the other featurizers will give you even larger number of features. You have got to be smart, and you have to choose the subset of available features. If you start to use all of the features, there is a pretty good chance that especially if your data set is small, you are going to end up into overfitting type of challenges. Okay, so since we converted the CSV data into JSON, I just wanted to give you an idea of how that looks. So in the CSV data, all we had was the composition, and we had over here the crystal structure. So in this particular problem, I'm only showing you a small subset of the database. So in this particular problem, we were denoting the crystal structure by one hot encoding. So we had, I think, 0 for hexagonal close pack, we had 1 for FCC, we had 2 for BCC, and so on and so forth. So as it turns out, the part of data set that I have grabbed over here is the part where you had all of this same type of crystal structures. Now, if you look into this JSON file, you will see that this is essentially a hierarchical storage of the data. It tells you that if I'm looking at one particular type of alloy system, so here basically what I've got is the NB titanium vanadium, aluminum 0.25 NB titanium vanadium is the common part, and then after that I am simply adding molybdenum or I'm adding hafnium, and as a result of that the crystal structure is changing. So I am storing the data in a very hierarchical manner in a JSON file. Okay, so this was just an aside. So once you have actually constructed the composition based feature vectors, next step would be to do the machine learning model. So now before we actually go to the next part, what I would want to do is I would actually want to give you a brief overview of the different types of featurizers which are available in this CBFE package.